For decades, aircraft designers assumed speed problems came from engines and materials. When planes failed at high speed, they added thrust, reinforced structures, and accepted rising drag as inevitable. Robert T. Jones questioned a simpler assumption. What if the wing itself was presented to the air in the wrong way? That single question led to one of the most important aerodynamic breakthroughs of the jet age. Robert T. Jones entered aeronautics at a moment when aircraft performance was advancing rapidly, but unevenly. By the late 1930s and early 1940s, engineers had learned how to build stronger airframes, more powerful engines, and more reliable systems. Yet, as speeds increased, progress became increasingly inefficient. Aircraft gained power, but drag rose faster. Structural loads increased disproportionately. Performance improvements required greater sacrifices with diminishing returns. At the time, aerodynamic theory treated wings largely as two-dimensional problems extended into three-dimensional space. Designers focused on airfoil sections, thickness, camber, and lift coefficients. High-speed issues were often blamed on compressibility effects that were assumed unavoidable. The prevailing belief was that drag rise at high speed was a consequence of physics that could only be managed with more power or stronger structures. Jones approached the problem from a different direction. Rather than asking how to push more air over the wing, he asked how the wing interacted with airflow in three dimensions. He focused on how airflow moved not just over the wing, but across it, particularly at high speeds where compressibility effects became dominant. His insight was that the wing did not experience airflow as a single unit. Instead, each spanwise section of the wing encountered air at a different effective speed and angle. This distinction mattered. As aircraft approached high subsonic speeds, airflow normal to the leading edge of the wing accelerated rapidly. Shock waves formed when local airflow exceeded the speed of sound, even though the aircraft itself remained subsonic. These shock waves increased drag dramatically and disrupted lift. Traditional straight wings presented a full free-stream velocity directly to the airfoil, intensifying compressibility effects. Jones realized that the key variable was not aircraft speed alone, but the component of airflow, perpendicular to the wing's leading edge. If that perpendicular component could be reduced, the wing would behave as though it were flying slower, without actually reducing aircraft speed. The solution was geometric, rather than mechanical. By sweeping the wing backward, the effective airflow normal to the leading edge decreased. Although the aircraft maintained the same forward velocity, the wing saw a lower effective Mach number. This delayed shock formation reduced drag rise and preserved lift characteristics at higher speeds. Crucially, this improvement did not require changes in engine power, materials, or structural strength. It was a reframing of the problem. Jones developed this concept while working with the National Advisory Committee for Aeronautics, NACA, the US organization responsible for fundamental aeronautical research. His work was analytical and theoretical, but it was grounded in physical reasoning rather than abstract mathematics. He did not arrive at swept wings by accident or intuition. He derived the effect from first principles of airflow behavior and vector decomposition. At the time, swept wings were not widely accepted as a high-speed solution. They had been considered previously for structural or stability reasons, but not as a systematic method to control compressibility effects. Many engineers viewed sweep as a compromise that introduced structural penalties and low-speed handling issues. Jones's work reframed sweep as a deliberate aerodynamic tool. His analysis demonstrated that sweep directly addressed the root cause of high-speed drag rise rather than its symptoms. This insight had immediate implications. Aircraft could achieve higher speeds without encountering catastrophic drag increases. Shock formation could be delayed without thinner wings or extreme power increases. Performance gains became achievable through geometry rather than brute force. The idea was radical because it challenged how engineers thought about speed. Speed was no longer a single scalar quantity to be maximized. It became a vector problem, one that could be managed by orientation rather than force. Initially, Jones's conclusions faced skepticism. Swept wings introduced new challenges: reduced lift at low speed, longer takeoff distances, and more complex structural loads. But these were engineering problems that could be solved. The alternative, accepting transonic drag rise as inevitable, was not acceptable for emerging jet aircraft. As experimental data accumulated, Jones's analysis proved correct. Wind tunnel tests confirmed that swept wings delayed compressibility effects and reduced drag at high speed. Aircraft incorporating sweep demonstrated superior transonic performance compared to straight-wing designs with similar power. By the end of World War II, jet propulsion had matured enough to exploit this aerodynamic breakthrough. Without swept wings, early jets would have remained trapped below their theoretical speed potential. With sweep, high-speed flight became controllable, efficient, and scalable. Jones did not design a specific aircraft. He provided a framework that reshaped aircraft design across generations. Fighters, bombers, and later commercial jets adopted swept wings not as stylistic choices, but as aerodynamic necessities. The jet age did not emerge solely because engines improved. It emerged because airflow was finally understood in 3 dimensions. Robert T. Jones did not overpower the air. He reoriented the aircraft to work with it. That shift, simple in concept, profound in consequence, redefined the limits of speed and became one of the foundational principles of modern aviation. The true significance of Robert T. Jones's swept wing theory became clear only when jet propulsion entered operational aviation. During the final years of World War II and immediately afterward, aircraft designers gained access to engines powerful enough to push airframes into the transonic regime. This exposed a critical problem. Jet engines could deliver sustained thrust at high speed, but straight-wing aircraft could not exploit that power efficiently. Drag rise, shock formation, and control degradation remained dominant limitations. Early jet aircraft confirmed this mismatch. Prototypes reached higher speeds than piston engine aircraft, but performance gains stalled rapidly as they approached Mach 0.8 to 0.9. Fuel consumption increased sharply. Acceleration flattened. Control margins narrowed. Engineers initially assumed these issues were inherent to early jet technology. Jones's work demonstrated that the airframe, not the engine, was the primary bottleneck. Swept wings provided a way to unlock the potential of jet propulsion. By reducing the component of airflow perpendicular to the wing's leading edge, sweep delayed the onset of compressibility effects. Shock waves formed later, drag rise was reduced, and lift characteristics remained usable at higher speeds. This allowed aircraft to cruise closer to the limits of the engine without entering unstable aerodynamic regimes. The US military was among the first to apply this insight at scale. As jet fighters became central to post-war air defense and Cold War strategy, speed was no longer a marginal advantage. It became a requirement. Interceptors needed to climb rapidly, accelerate quickly, and operate near transonic and supersonic speeds without unpredictable behavior. Straight-wing jets could not meet these demands reliably. Aircraft such as the North American F-86 Sabre demonstrated the operational value of swept wings. Although multiple factors contributed to the Sabre's success, swept wing aerodynamics were essential to its high-speed performance. The aircraft could maneuver near transonic speed with greater control stability and lower drag than straight-wing counterparts. This translated into practical combat advantages rather than theoretical performance gains. Importantly, the swept wing did not eliminate all aerodynamic challenges, it shifted them. Sweep introduced new issues at low speed, including reduced lift coefficient, higher stall speed, and more complex stall behavior. Takeoff and landing distances increased. Aircraft required higher approach speeds and more careful handling near stall. These trade-offs were real, but they were manageable through engineering solutions such as high-lift devices, leading-edge slats, and improved flight controls. The key distinction was this: swept wings made high-speed flight achievable, and low-speed problems could be engineered around. The reverse was not true. No amount of engine power could compensate for uncontrolled transonic drag. As swept wings became standard, aircraft design philosophy changed. Engineers no longer optimized wings solely for low-speed lift or cruise efficiency. They optimized for performance across multiple speed regimes, with particular attention to transonic behavior. Wind tunnel testing expanded to focus on shock formation, pressure distribution, and spanwise flow effects. Jones's contribution also influenced how engineers thought about stability and control. At high sweep angles, airflow tended to move outward along the wing, increasing the risk of tip stall and loss of aileron effectiveness. This forced designers to consider wing twist, airfoil variation along the span, and control surface placement more carefully. These refinements deepened aerodynamic understanding rather than simplifying it. Beyond fighters, swept wings became essential for bombers and reconnaissance aircraft operating at high subsonic or supersonic speeds. Strategic aircraft required long range efficiency combined with speed. Swept wings reduced drag penalties during cruise and allowed sustained high-speed operation without excessive fuel burn. Again, the benefit was systemic rather than isolated. Jones's ideas spread rapidly because they were grounded in physics, not doctrine. The swept wing was not tied to a specific mission or aircraft class. It addressed a universal aerodynamic constraint. Once validated, it became unavoidable. Aircraft that ignored sweep were increasingly obsolete in high-speed roles. By the early Cold War, swept wings were no longer experimental. They were baseline architecture. Designers debated degrees of sweep, structural optimization, and control integration. But the fundamental principle was settled. The airframe had to be oriented to manage airflow, not resist it. Robert T. Jones did not push aircraft through the sound barrier by force. He made the barrier negotiable. His work ensured that jet propulsion could evolve into a practical, controllable, and scalable technology. Without swept wings, early jets would have remained fast curiosities with limited operational value. With them, high-speed flight became routine rather than hazardous. The transition from theory to aircraft marked the moment Jones's insight stopped being an academic solution and became a foundation of modern aviation. Robert T. Jones's influence on aviation did not peak with the adoption of swept wings on early jet fighters. It deepened as aircraft design matured and speed became a permanent operating condition rather than an experimental threshold. Once swept wings proved their value, they stopped being discussed as an innovation and became structural assumption. That transition is precisely what made Jones's contribution both decisive and largely forgotten. As aircraft entered sustained high-speed regimes, designers no longer asked whether wings should be swept. They asked how much. Sweep angle became a parameter to optimize rather than a concept to debate. This shift marked a turning point in aerospace engineering. Jones's idea had moved from discovery to infrastructure. The swept wing reshaped the entire aircraft development process. Structural design had to adapt to new load paths created by sweep. Wings experienced increased bending moments and torsional loads, requiring stronger spars and refined materials. This pushed advancements in structural analysis and fatigue modelling. Aerodynamics and structures became more tightly coupled disciplines rather than parallel concerns. Flight control systems also evolved in response. Swept wings altered stall behaviour and roll response, especially at high angles of attack. Engineers introduced new control strategies, differential spoilers, and refined aileron designs to maintain handling quality. Later, these challenges accelerated the adoption of powered controls and stability augmentation systems. The path toward fly-by-wire began with problems introduced by high-speed aerodynamics. Jones's influence extended directly into supersonic aircraft development. While swept wings alone were not sufficient for efficient supersonic cruise, they were essential for managing transonic acceleration and reducing drag near Mach 1. Aircraft such as the F-100 Super Sabre, B-47 Stratojet, and later supersonic platforms depended on swept-wing principles to function safely and predictably during acceleration and maneuvering. Strategic bombers highlighted the importance of Jones's work at scale. Long-range aircraft operating near transonic speeds required aerodynamic efficiency to achieve mission range without excessive fuel penalties. Swept wings allowed bombers to cruise faster while maintaining acceptable fuel consumption and structural margins. This capability shaped Cold War air strategy, where speed and reach mattered as much as payload. Civil aviation followed the same aerodynamic logic. As commercial aircraft grew faster and heavier, swept wings became unavoidable. High subsonic cruise near Mach 0.8 offered economic advantages only if drag rise could be controlled. Swept wings made modern airline operations possible by balancing speed, efficiency, and stability. Every jet airliner owes its basic wing geometry to the insight Jones formalized decades earlier. Despite this, Robert T. Jones remained largely absent from public narratives. He did not lead major aircraft programs or attach his name to a specific airplane. His work existed at the level of configuration rather than product. This made it universal, but also anonymous. Engineers inherited his ideas as standard practice rather than historical innovation. Within engineering culture, Jones was known for his clarity of thinking rather than institutional authority. He challenged assumptions, reduced complex problems to their governing principles, and resisted solutions based on brute force. His swept-wing insight reflected this mindset. Instead of fighting airflow with power, he reframed the interaction between air and structure. This approach influenced generations of aerodynamicists. Jones demonstrated that many perceived performance limits were artifacts of perspective rather than physical law. When systems fail at scale, the failure is often architectural. Changing orientation can be more powerful than adding strength. The invisibility of Jones's legacy is a measure of its success. Modern aircraft designers no longer question whether wings should be swept for high-speed flight. The decision is embedded so deeply that it no longer appears innovative. This is the final stage of engineering influence, when an idea becomes indistinguishable from necessity. Robert T. Jones did not make aircraft faster by discovering new materials or engines. He made them faster by asking a different question about geometry. That question reshaped aviation permanently. Every jet aircraft that accelerates smoothly through transonic speed carries his solution in its silhouette. The swept wing is not a feature. It is the quiet architecture of modern flight. Jones did not defeat speed limits with force. He changed how aircraft meet the air. And once that change was made, aviation never went back.